Welcome everyone. Thank you all for joining the RISE ECE Computer Engineering Distinguished Speaker webinar. So before I introduce our speaker today, let's briefly go through some logistics. So first, if you have questions during the talk, you can message me in the Q&A chat at the bottom of your Zoom window. At the end of the talk, we will select those questions to be addressed by our speaker. At the same time, if you have questions during the talk, then I think it makes more sense to be addressed during the middle of the talk. I will also monitor the Q&A chat window. So second, this talk will be recorded and uploaded to our department's YouTube channel for future access. And next, it's my great pleasure to introduce today's distinguished speaker, Dr. Deming Chen, so who received his PhD from UCLA and is the Abel Bliss professor at my alma mater, the University of Illinois at Urbana-Champaign. His research interests include system-level design methodologies, machine learning accelerator, reconfigurable computing, and hardware security, for which he has received 9 Best Paper Awards. In particular, he and his students have made pioneering contributions to machine learning accelerations in FPGA, especially via algorithm hardware code design, evidenced by their Best Paper Award in ICCAD 2018, and the first place winner in both the FPGA and GPU categories of System Design Contest at DAC 2019. Dr. Chen is an IEEE Fellow and also ACM Distinguished Speaker. In addition to his exceptional track record in research, he has been involved in several startup companies, including co-founding the In-Spirit IoT, which design accelerations for machine learning targeting IoT industries. Thanks a lot, Dr. Chen, again for accepting our invitation, and the rest is all yours.
Okay, yeah, thank you very much, Professor Lin. And yeah, so you mentioned UIUC as your alma mater, right? So you and I, we actually on the same floor of the same building, and we often run into each other. And right, so I'm very happy that I would have this honor to give this presentation, right? And then the title of the talk is Elegant and Effective Co-Design of ML Algorithms and Accelerators. So by the way, so as mentioned by Professor Lin, right, so if you have questions, feel free to ask. I don't know whether you can verbally ask. If not, you can enter the question into the chat window, and I will be very happy to answer them, right? So this can be very interactive. Okay. All right. So we are talking about AI, right? So AI has been a hot topic, right? So if you look at the roadmap for AI, I summarize 4 dimensions, and they actually convolute together to deliver where we are, right? So the first one is big data, right? So nothing new. Every day, a large amount data set flood us, right? And Facebook and Google and etc. Twitter, right? And millions of followers and all that, right? So they just provide very naturally raw material to train the machine learning models, okay? And then the second dimension is cloud computing, okay? And so instead of buying a huge cluster, right, in your backyard, people can afford to access computing in the cloud, right? So it becomes more affordable, right? And then more scalable. The third one is the development of deep neural networks, right? So we all know deep neural network was not a new concept, right? It was invented close to 80 years ago, right? However, although in the early years people had very high expectation, it didn't really deliver due to various type of limits. But then until very recently, about 8 years ago, right, we had a big breakthrough, right? AlexNet was invented, and it won the ImageNet challenge, and then the rest is the history, right? So these days, there are so many deep neural networks invented for different types of applications, and it's really driving the innovation forward. And by the way, this little cat belonged to me. Okay, so you probably remember that Google did some study trying to recognize cats, right? So this was about 6-7 years ago, so, right? And then people realized, oh, okay, actually recognizing cat is very scientific, right? So that really leads to a lot of new breakthroughs, including Google AlphaGo winning the world championship for the Go game, right? So this is really going forward in an exponential speed, okay? And then finally is the hardware advance, right? So this include GPU, right? So this is NVIDIA CEO, Jensen Huang, and then FPGA, right, offered by both Xilinx and Altera, and then Google, TPU, and then many other companies, right, so really pushing the frontier of the hardware design. Okay. All right, there is always a but, okay. So we are also facing big AI challenges. So the first one is this huge compute demand, right? So here is x-axis is the time, right? And then the y-axis is the computing need, okay? And this unit is interesting. It's a petaflop, right? So this is 10 to the 15th. It's a huge number. And so let's say you deliver petaflop computation per second and you run for days, right? And that's how much computation is needed to train these huge models, such as AlphaGo 0 or AlphaZero, okay? So then people are wondering, from the computation need, I mentioned AlexNet already, right? It's around 2012. And then AlphaGo is about 2017, right? So it's about 5-6 years. What's the difference? The difference is 30,000x. So this speed is, first of all, definitely it's exponential. Second of all, this is even faster than Moore's law, right? So the computational need double every 3 months. Okay, this definitely is not good news, right? If we do not deal with this challenge, it's actually not even good for environment because it will generate a lot of heat, okay, and it consume a huge amount of electricity, okay. So on the left side is on the training, right? So we all know the computation need for training is huge, but how about inference? That means, okay, the models are trained, so we are going to use it for classification and different type of applications. And then you can see the computation need for inference also is very large. So here, the y-axis is the accuracy, right? So this is the model accuracy. And x-axis is the operations, right? This is a giga operations, right? And then you can see when we increase the accuracy, the model is becoming larger, okay? And definitely this is not complete, right? So these days there are models that are doing natural language processing and transformers, and those can become much larger than this, okay? So then the second challenge is the massive memory footprint, right? So then this is quite intuitive. You have a huge amount of computation, and then you are crunching the data. Then of course, to make sure the computation is fast, we do need to deal with memory, right? So then you can see, again, when the models are advancing, the number of parameters for the model are increasing, and the total number of total amount of memory is also increasing in an alarming way. Okay, and then let me just use one example. So this is VGG16, right? So if you look at the convolutional layers, right, it has suppose, so here we have 13, right, 13 conv layers, and then starting from conv2, the feature size, right? So this is the not the parameter anymore. The parameters are the weights, the kind of kernel weights. These are the feature maps. These are the intermediate results that are passed across the deep neural network. And then, if you are dealing with high definition, so these days high definition is actually no longer 1080p. It can become a 4K, right? For certain applications where you need a lot of pixels to deliver the quality of results. But then let's say just dealing with 1080p, then for this single layer, we need more than 250 megabyte, right? So this can become a huge challenge for a lot of computational platforms, right? So this indeed is another challenge, especially if we are working on edge devices, which usually do not have like a large on-chip memory, and then it also has very limited external memory access bandwidth. Okay, so the third challenge is the real-time requirement. So actually, a lot of AI applications require real-time, right? Autonomous driving requires real time, right? And if the decision is not made in time, we may face a life or death situation, right? So of course, different applications have a different real-time requirement, but typically when you apply real-time requirement, we have very strong constraints. Okay, so let's say the real time is 30 frames per second. And then if you look at all these different deep neural networks that people have developed through the years, and then we evaluate them on top of this embedded system, right? This TX1, right? We are talking about edge device. And then not many models can really fall into this region. And then for the models that do fall into this region, the accuracy is not as high as others, right? So that's the third challenge, right? So how do we really deal with these challenges? So we are engineering students, so we all know when there are challenges, there are also opportunities. Okay, so let's talk about some effective ways to deal with challenges, and hopefully at the end of the talk, I also convince you that we come up with some elegant ways to deal with challenges. Okay, so what can be an effective solution? So let's talk about the effective solutions. Okay, and so we can look at the existing solutions, right? Typically, these are top-down, right? Independent AI algorithm and accelerator design. Okay. However, there are severe drawbacks for edge AI. Okay, I'm going to elaborate pretty soon. And then we are going to talk about a new design methodology for edge AI. So this is the topic of the today, which is algorithm and hardware accelerator co-design. Okay. So let's look at this kind of conventional top-down DNN design and the deployment kind of strategy. So we are looking at several key metrics, right? These include accuracy, right? We all care about accuracy. The model has to be accurate in order to deliver some good decisions, right? However, because we are talking about edge devices, and right, then we are facing stringent latency, throughput, energy, power, hardware cost constraints, right? So then let's look at this top-down model. Typically, people will kind of start to design DNNs using some popular platforms, right? So most of you probably are familiar with TensorFlow or PyTorch, and right? And then train the model, right? Design and train the model, and then going through some software-related optimizations such as quantization, pruning, and layer fusion, etc. Okay, and then after that, we have to map the software to the hardware, right? So on the hardware side, there are also optimizations such as parallel factor, right? So if you can parallelize the computation, of course, it can become faster, but you have to honor the resource constraint and etc. And then eventually map to the specific hardware. And then you can see there can be iterations between the software and the hardware, right? This is more like a try and error. Okay, so I try a bunch of software optimizations, and then I see whether hardware will like it or not. If they do not see eye to eye, and I have to go through these multiple iterations, because when you are trying to optimize one piece of code, you do not really know what it means towards the hardware implementation, because all these are considered independently, right? Okay, so then obviously there are drawbacks, right? So because when we are dealing with software metrics, we are talking about this group of metrics. When we're dealing with software development, right, we are talking about this group of metrics. But when we are trying to map that to the hardware, we are talking about different metrics. They may not agree with each other, right? So then also it's difficult to select appropriate reference DNNs at the beginning, right? So it's almost like a dark magic. You have to choose by experience, and right, and then try some on the published data sets, etc. Overall, it's quite lengthy. Okay, so this graph is demonstrating the challenge in more detail. Okay, so then you can see we are dealing with this long iterative procedure, tedious engineering effort, right? So let's see, we do the software model. It's already a kind of complicated process. And then we try to map it to the hardware. The hardware, we know hardware is even more complicated. And if they do not agree with each other, then you have to go back, right? So it's very hard to converge, and also it's suboptimal. Okay, so then that's why we need a DN model and accelerator co-design. Okay, so what is simultaneous AI algorithm accelerator co-design, right? So let me summarize this topic in this single slide. Okay, so traditionally, as we have talked, hardware and software are designed independently. So if we look at this picture, so the algorithm design can be optimized, right, step by step, and but along the way, the accelerator is fixed. Okay, and then for the simultaneous algorithm accelerator co-design, both the algorithm and the accelerator design spaces are parameterized and co-searched simultaneously. So you can see the software are changing, being optimized, and along the way, we have a bidirectional co-search strategy. The hardware is co-designed. Okay, and then at the end, both the optimized algorithm and its hardware implementation also optimized. Both of them are produced simultaneously. Okay, so let me go through a little bit of history. So actually, as far as we know, we proposed this algorithm and hardware co-design in 2018 through a kind of conceptual paper published at ICSICT. Okay, and then after that, we kind of build on top of this idea, right? And then published several papers, and including DAC 2019, ICCAT 2019, and then also MLCs and that paper this year. So I do not have time to go through all the details. And for this talk, I will mainly focus these last two pieces of work. And also due to the time limit, I may not have a lot of time to go into all the details. However, if you have questions, we can definitely come back to certain slides and then go deeper on certain areas. Okay, but I can summarize the idea, right? So I talk about this co-design method proposed in ICSI CT 2018, right? So this is a invited conceptual paper. That's where we propose this idea, okay? So I will not go into these details. So here you can see the inputs include both the constraints, this hardware side, and then software side. Software side, including the algorithm building blocks. We call it the IP pool and the target application. And then we go through this co-design engine, and then we can produce solutions. And the solution will include both hardware and software. So this is quoting from the paper. So the co-design is to automatically generate both DNN models and their corresponding implementations as pairs, and shorten the DNN development time by avoiding tedious iterations between DNN model and its accelerator designs. Okay, and then we start to build up on top of this concept. And so the first paper is a first real paper, right? So it's materialized in DAC 2019. And then we basically take this bidirectional co-design approach where the DNN can drive the hardware design and the hardware design can drive the DNN design, right? So they are co-designed simultaneously. As I mentioned, indeed, we are using these pairs, and then eventually it is still iterative, okay? However, it can converge much faster, and eventually both are delivered with high quality. Okay, so we actually build a detailed flow and to enable that, but I will not go into the all these blocks. And so in summary, we have an auto DNN that can search the DNN design space, and we also have auto high-level census. If you have looked into high-level census, this is a high-level design methodology where we can take the algorithm, right, and then generate hardware through auto high-level census. The hardware is using the tile architecture, and then the auto DNN is using some DNN template, and eventually we generate both software and hardware. Okay, all right. So let's focus on this SkyNet. So Professor Lin mentioned that actually we won the championship through SkyNet in DAC 2019, right? So this is a system design competition. And so I will quickly go through the design methodology of SkyNet, okay? So there are mainly 3 stages. Okay, so the first one is to pick the basic building blocks. Okay, so this building block is representing both the algorithm and the hardware. So I will elaborate more, right? So what we do is we have a DNN component, right? We can figure out the most popular suitable DNN components. So luckily, many DNN models are quite regular. Okay, and then based on this, right, so this become a building block, then we can come up with some bundle design. Okay, so bundle is like a group of DNN operations that can deliver some functionality. And then because each of these building block has its corresponding hardware IP design, so once we pick a template for the algorithm, we also know the hardware implementation pretty much, right? So that's how we can code it on both, right? So this is a more like how to say engineering approach, but it's very effective. Okay, so that's the first stage. We will design the bundle, and then we go through some design space exploration, come up with Pareto curve, so we have effective trade-off, and then we can further fine-tune the bundle, right? And this really depends on the particular application we have. And then after all the bundles are finalized, and then we have, this is more like a post-processing to further improve the quality. Okay, so let's look at this bundle, right? So I have already spent some time to talk about it. So this can be a bundle, right? So convolutional 3x3, depth-wise convolution 3x3, convolution 1x1, activation, right? So the configuration can change. Okay, so then this bundle can be used to build a DNN, right? So let's see, this is my first bundle. And then the second bundle, it's a similar structure, but I can expand the channel, the number of channels, and right, I can add a pooling layer right here and there. Right, you can do some fine tuning. And as I mentioned, for each of these bundle, we have rather so corresponding hardware implementation. So this bundle is almost like a mediator between the software and the hardware to make sure they are friends. So they are not enemies. They do not fight with each other. Okay. All right. So we also have a tile architecture for the hardware. Okay, so we know hardware design is very important. Even I can have a very good software. If I do not have a hardware optimization, the end result cannot be good. Okay, so here we have inter and intra-layer IP reuse. What does that mean? Okay, so we are using FPGA as a prototype, but a lot of these ideas can be applied to ASIC. Okay, so you can see the feature map can be large, right? So as I mentioned at the beginning, right? So the VGG16, the feature map, if you just want to store the whole thing, is huge. So we have to divide and conquer, right? So we come up with a tile architecture. So then we can do tiling on top of the feature map. Then once you have the tiles, then you can do a pipelining, right? Pipelining across 5 stages. So this is similar to a customized processor, right? Then you have the data, you load the data, you do the convolutional computation, etc. in a pipelined fashion. So once you do that, then you can actually reuse the IP, and pipelining can improve the overall throughput. Okay. So then let's quickly go through this step and the steps because I already mentioned it right at the beginning, right? So this is the first step. As I mentioned, we will enumerate the bundle, we evaluate them, okay, and then we select those in the Pareto curve, which means if you have a high accuracy, right? So then that means if this bundle has high accuracy, then most likely I will pick it even when its latency is larger. Okay, so let's see. This is bundle. Okay, so here is the Pareto curve, right? So here is the Pareto curve. So then you can see if I have high accuracy, let's see the accuracy here, then I can afford to have a longer latency, right? However, if, for example, for this one, right, its accuracy is not as high, right? So its accuracy is similar to this point, but then its latency is longer than this point, then this point is cloned, right? So that's what it means by Pareto curve, right? So we'll do the characterization and we'll pick the points on the Pareto curve. Okay, so then once I have that, then we go to the second stage. So we are facing a multi-objective optimization problems, right? So we actually stack the bundle together, right? So this is inspired by actual deep neural model, deep neural network design. For example, ResNet is like a bundle design, right? So all the layers are similar, and you just stack them together. And by the way, ResNet is still one of the best kind of deep neural network, right? So we follow the strategy. However, we can fine tune it, right? So for example, here we can, for these things, different, so it's the same bundle structure, but we stack them for each of the stack, right? We can have potential channel expansion, and then across the different bundle, we can insert the pooling, right? So then this become a hyperparameter that we can use to drive the DNN design. Okay, so this is automated, right? So then what we did is we actually come up with a fitness function, and we adopt a algorithm, so-called particle swarm optimization, right? So it's one type of evolutionary algorithm. Okay, so what's the fitting function, right? So it's actually quite straightforward. We'll consider both the model accuracy and the latency, right? So then this is the algorithm, and this is the hardware implementation, and we just put them together, right? So this is not very elegant, but it's actually quite effective, right? So if the fitness function is good, then we pick this particular DNN. Okay. All right. So how does the PSO work? Okay. So we actually consider a pair of high-dimensional vector, right? So these are the channel expansion and pooling insertion, right? So we'll change this to change the actual DNN. Then we use this particle swarm optimization. You know, it has both local based and group based. So it tries to capture some kind of global optimization, right? So trying to avoid some local optima, right? So this is any search algorithm, whether it's a simulated meaning or evolutionary algorithm, we have to deal with being stuck at the local minima, right? So in order to escape the local minima and try to get a global optimization, right? So the details are in the paper. So, but this search algorithm is actually quite effective, and then we can pick the best candidate through this PSO algorithm. Okay, so then after that, we have this post-processing step to further improve the DNN design. Okay, and then after all the steps are done, right? So let's look at our overall system. This is built on top of the FPGA, right? So the FPGA has embedded CPU. So then we have image coming in, go through the pre-processing that can be done in the embedded CPU. Okay, and then we have the hardware design, right? So we have the algorithm, and we have the actual hardware implementation. All these are done on top of the FPGA using logic. And then we have the BRAMs, and we go through this accelerator design, right? So overall, we actually obtained very good results. So let's look at some details about this DAC competition, right? So it's object detection using drones, okay? And it has two categories, both GPU and FPGA, and both are embedded systems. Okay, so it targets single object detection for real-life UAV applications. Okay, and the images contain 95 categories of target objects. Most of them are actually quite small, and then there are comprehensive evaluation criteria, including accuracy, throughput, and energy consumption, right? So throughput energy consumption, of course, makes sense for the edge device. And then in the same time, people still want to maintain accuracy in order to be useful, okay? So then what we did is we analyzed this DAC-SDC data set, right? So it's quite unique. And so here, if we look at this graph, right? So the x-axis is area of output box over area of input image, right? So 1%, that means this object is just 1% of the overall input image, which is very small. And but look at through, when we look at all these different objects, we realize 31% of the target object is actually less than 1% of input size. Okay, and then if we look at less than 9%, and then more than 91% of the object fall into this category, right? So if you look at this video, then you can see indeed the objects are very small, right? So for example, here, this is actually a person riding on a horse, right? So if we do not look at it carefully, we don't even know. And then this one is not trying to detect the boat. It's actually detecting this person who is being dragged along, right? And so the challenge is actually quite high. So what we did is we go through the SkyNet data methodology and we produce this deep neural network. It's also called SkyNet. By the way, all these are open source, right? So if you are interested, you can definitely download and start to build on top of it. And right, so this is the final model. You can see we have the bundle, right? So and we also have the pooling, inserted. And then we added some additional features such as a bypass, so then the features can bypass some convolutional layer, bypass pooling layer. So because the objects are very small, right? So if we bypass, we can still maintain the size of the objects. And then you have the both original kind of object feature map pass through this model and the bypassed one. And then you have more information to work with, right? So that typically can help in terms of bounding box regression. Okay, so then we can deal with system level pipelining, okay, and then we can target both GPU and FPGA. All right, so let's look at the results. So here I collected 2 years of competition results for 2019 and 2018. So then you can see these are the GPU results. So then 2019 results are better than 2018 results. Similarly, right, 2019 FPGA results are better than FPGA 18 results. Right, so here the higher the better. Here the higher the better. Right, so then let's look at our result. This is SkyNet GPU, right? So this is the same competition, same year, and we are 2.3x faster. Okay? And then if we look at the FPGA results, and we are actually 10% more accurate compared to the second place. Okay, so indeed, this co-design method is very effective. Okay, it's not very fancy, but effective. Okay, so then later on, we also extend the SkyNet to real-time tracking problem. So tracking is different from detection, right? So if we take a look at this tracking video, then you can see the object can be occluded. That means it's hidden, right? And it can run with different speed and size are changing, angle are changing, right? So it's actually more complicated than detection. Okay, so typically people will use some neural network as the backbone to drive the tracking algorithm, right? So then we evaluated the two existing tracking algorithms using SkyNet as the backbone instead of ResNet 50. Okay, so the AO is average overlap. So the higher the better, right? So this is similar to the IOU, right? So okay, I have the ground truth and I predict the area, right? So the predicted area and the ground truth, the more overlap, the better, right? So that means the more accuracy. And the more accuracy, right? So then this SR means a success rate, right? So this means if the IOU is 0.5, so basically the overlap is 0.5, what's my success rate? Also, the higher the better. And then we can see this is similar, right? And this is slightly worse. Okay, this is similar, but we are much faster. Okay, and then here same thing. So we are actually slightly better. This is also slightly better, and in the same time we are faster. Right. So indeed, this co-design methodology is validated and it's working. Okay, so let me stop here. Any questions so far?
I think there is already one question, but not related to this work. I think this audience, Yan Yi, he probably read your paper before, and he typed this question at the very beginning. Yeah, maybe you can proceed, and we can address those questions at the end.
Okay, sure, yeah. And
Thank
let me
you.
check the time. Okay, good. So I think we are still good with time. Okay.
Yes.
So then the question now is the co-design problem solved? You probably guessed actually it's not. So in SkyNet, DNN and its accelerators are searched coordinately, right? And it's coarse-grained, right, efficient, but still kind of greedy, okay? And the algorithm can explore limited co-design space. Okay. So then the next question is there a more elegant way for co-design space formulation and search? So our goal is to form a new unified and holistic co-design space and search the co-design space systematically and thoroughly. Okay. So that's how we developed the EDD. Right? So you probably heard about BDD, right? So but this is a EDD. So efficient differentiable DNN architecture and implementation co-search. What does it mean? What does it mean? Okay. So the key idea is to define the algorithm search space and the hardware implementation search space together. We actually mingle them together in an elegant way, and then we can search the co-design space in an elegant way as well. Okay. So let's see, we have this neural architecture search space A, and then we also have the implementation, right, hardware implementation search space, which is I. Okay. So then previously, for SkyNet, we are kind of exploring both space simultaneously, but we didn't really model this combined space well. Okay, so now what we can do is we try to model this combined neural architecture and implementation co-search space. Right, so it's A and I. Right, so then if we can formulate it as differentiable, and then we can solve this problem using gradient descent. Right? So once it's differentiable, then we can just apply this very popular, useful gradient descent methodology to search both space. Okay, so let's look at the existing work formulation and then our proposed co-design formulation. So existing, right? So as I mentioned before, we have A is differentiable, right? So this is loss function, and then the hardware is fixed. Okay, and then now what we do is we will consider both A and I, right? So remember the implementation can contribute to accuracy as well, right? So a simple example is to quantize your algorithm, right? So if I quantize it down to 2 bits, of course, implementation is very efficient, but then your accuracy will for sure degrade, right? So that means both A and I will contribute to the accuracy, and then I will contribute to the performance. So then now we have a performance loss, okay? And then we also need to honor the resource constraints of the hardware, okay? So then all this need to be considered simultaneously. Okay, so the challenge is now how to formulate I as differentiable with respect to the loss function, right? Okay. So if we combine all this together, so we also try to divide and conquer and multiple stages. And so we will have neural architecture search. Okay. So this time we adopt a popular neural architecture search that's using a supernet, right? So the supernet is kind of embedding multiple different scenarios, okay? And then you train the supernet. The supernet is differentiable. You train the supernet, and then after that, you can sample some subnet out of the supernet, and each subnet can become the final neural network, right? So this is a so-called differentiable neural architecture search, okay? And then using this framework, okay, right, so differentiable neural architecture search, on top of this framework, we will add differentiable implementation search, and then we can co-search the combined space, right? So that's the idea. Okay, so let's look at the differentiable neural architecture search, right? So typically, right, so this is a simplified version, right? So you will have a supernet, and then it consists of various type of blocks, okay? And then each block, if we zoom in, it has inputs, right? So this is the tensor, outputs is the, tensor after the computation. And then we can have multiple different operations. And here, each operation is similar to the bundle I talked about before, okay? So then this actually connect both works very naturally, right? So in our implementation, we can use the bundles, right? So, but then different bundles, right? Different operation represent different bundle. That's how this differentiable neural architecture search can really embed different solutions. Okay? So, however, in order to make the search differentiable, we need to play some tricks, right? So this already done by existing work, right? So this idea was introduced by FPGA, right, last year. So because each of these operations is actually discrete, to make it differentiable, people need to convert from discrete to continuous, and using this gumbo softmax function. Okay, so I will skip the details. The details are in the paper, and if you are interested, you can definitely read this paper too, right? So there is the sampling parameter. The sampling is basically sample. Okay, I'm going to use this operation or use a different operation within this block. I use the other operation within another block, right? So you can sample it, but follow this gumbo softmax distribution. Once you do that, you actually convert the discrete to continuous. Okay. And then we borrow the same idea into the implementation, right? So once we get into implementation, it looks like we have to do quantization, right? Quantization is very important, right? So then, okay, for this operation, which is bundle, I can pick one layer, and then I can decide what kind of quantization bits I can use to, first of all, optimize the implementation. Second of all, because the algorithm and the hardware is co-designed, and I know the final accuracy during the search. So because of that, I can pick the right quantization solution. So we use the gumbo softmax for this as well. And we can consider other hardware implementation scenarios, parallelization, loop tiling, and all this can be considered, okay? All right, so then we can come up with 4 stages, okay? So the stage 1 is really considering this fine-grained FPGA level hardware implementation, right? And including the quantization, right? And after that, okay, so this is the example here, okay? So you can see this quantization can be expanded into different equations depending on whether it's a convolution or depth-wise convolution. And then we can use the specific resource model, right? So this is for one particular Xilinx FPGA, right? But if it's ASIC or if it's an Intel FPGA, all this can be changed. So this is flexible, okay? And once we have the quantization and together with other hardware optimization built into this kind of, this is a single implementation scenario, right? For this bundle, right? So for this bundle, if we pick one quantization bit, it will be consistent across all these different sub operations, right? Then after that, I can summarize the overall solution for this block. Okay, and so this is bottom up, and then once I have this block, then I can summarize the overall solution for the whole DNN, right? So so basically the implementation and the algorithm are mingled very naturally in an elegant way. Okay, so we dealt with some other complications. For example, if we try to target end-to-end latency, then we can use the summation of all the blocks, right? However, if we want to deal with the throughput, then we try to minimize the largest latency across all the blocks, right? But however, because a maximum operation is not differentiable, then we use approximation, right? So this is a like a log sum approximation that can be differentiable, and still we can maintain the overall target optimization target. Okay, so we can also consider resource sharing, right? So resource sharing is very important, especially if your FPGA is not very large. Then we cannot allocate too much resource, and they have to share. Okay, so then this can be modeled through this hyperbolic tangent to compress the expectation into unit so this one means it's a unit expectation. Okay, all right, so let's look at some experimental results. Okay, all right, so I'm almost done. So we actually used this EDD and we searched on top of this code design space, and we generate a bunch of different EDD deep neural nets. Okay, the first one targeting GPU, second one targeting this recursive FPGA accelerator, which means I have the IPs that can be shared again and again. Pipeline FPGA is like, okay, if I have 5 layers, each layer will be mapped to its dedicated hardware, and then I pipeline across these 5 layers. It can produce high throughput, okay? However, it may not be the most kind of resource efficient, okay? So different ways. And then we searched on subset of ImageNet with 100 classes and test on the entire ImageNet trained from scratch. And you can see with different target, right? The EDD nets are quite different. Okay, although the building blocks are kind of similar. Okay, so here it is for GPU results, right? So we compared with the existing state of the art, and right. So there are baseline models. There are so these are designed by human, right? And so we can have top 1, top 5 air, okay? And these are designed by the NAS, neural net architecture search, right? So this is using machine to design the neural network, right? And they can be hardware aware, right? However, they are not co-designed. And we can see machine developed models actually have a higher accuracy compared to the human ones, okay? And our design has a similar accuracy, a little bit worse, but here, it's even better than this one. But most importantly, we are much faster. Okay, and then here this EDDNet2 is comparing to this recursive FPGA accelerator, And all these things are evaluated on top of the ChaiDN, right? So this is a open source deep neural network accelerator developed by Xilinx. Okay, so all these are evaluated on top of ChaiDN, and again, we have the shortest latency. Okay, and then we also compare against the DNN builder. So Professor Lin mentioned actually we won a best paper award with this work from ICCAT 2018 by EDD Net3 actually beat the results from DNN builder, and again we are much faster. And also, our error is lower too. Okay. So let's conclude this talk where we presented SkyNet and hardware efficient DNN design methodology. Okay, so for SkyNet, it's a bidirectional DNN accelerator design flow for embedded systems, and as I mentioned, it's quite effective. But then later on, we proposed the efficient differentiable DNN architecture, and hopefully I presented it in a way that you're convinced is also elegant. Okay, and we demonstrated 3DN models targeting low latency GPU, recursive FPGA, and pipeline FPGA accelerator. And indeed, this exciting research direction in the future can do co-design for distributed AI, for heterogeneous and large-scale AI, or emerging AI technologies. So, if you're interested in this area, I definitely encourage you to, carry out this research, right, to really innovate in this very exciting area. Okay, so finally, let me acknowledge other funding agencies and also my collaborators. Dr. Cong Hao is going to join Georgia Tech as an assistant professor next year, and she is one of the key developers for these works, and also my PhD students Xiaofan, Yu Hong, my other postdoc researcher Dr. Yao Chen, and other students. Okay, and I also would like to really remember Professor Tom Huang, right? So you probably all know he's considered as the father of computer vision, right? So Tom passed away several months ago. We really, miss him dearly. And also we collaborate with Professor Wenmei Hu and also IBM researcher, Dr. Jin Junxiong and Hong Hui Shi. Okay, so a researcher from Inspirit IoT also participated. Okay, that's it. Thank you very much. So now we can open for the questions.
Yeah, very enlightening talk. Thank you. I think we have received several questions in the Q&A chat. In case to our audience, in case you haven't got the chance to type your question, you can do it now, or you can raise your hand. I will unmute you so that you can speak your question. But before we talk about the question, I would like to share a few personal notes. As Dr. Chen mentioned, my PhD office just next to his. So during my PhD, I think there are several keywords. The first one about Dr. Chen, the first one is best paper. So during my time at UIUC, I think you received several best paper awards that often show up in the department news. Those, I think the audience probably also learn from news. But several observations. The first one is whenever we ran into you during the hallway, you always show up your very calm and nice smile. I think that's things I always remember. The second one I think is you always come to the office, I think around 7 a.m. every day. And then also come to the office during the weekend. I think that's very inspiring to me because I feel like you not just work hard, but also you love what you are doing. So I would like to share it, hopefully also inspire our students here.
Yeah, that means you also work very hard. That's why we could meet at the early hours, right?
Inspired by you, actually. Yeah,
Oh,
I
thank you.
realize you love what you are doing, but also very nice to us when we were student at that time. Um, so now we already received a few questions. I think Yuan Yu, he must be prepared. So he sent the latest comment saying, thank you for the presentation, very impressive work, but because his mic has some issue, he asked me to speak the question. So his question is, what's the problem size of the search algorithm named stochastic coordinate descent in the DAC 2019 paper?
Oh, okay.
So
Right,
he's prepared. He read your papers and came with questions.
right. Yeah. So that's a very good question. Let's go to that slide. You know, um, I didn't have enough time to talk about it, but this is one of the it's last year, but this field is moving so quickly, right? So what happened here is we indeed introduced the bundle already, right? So in this work, and the SkyNet is actually using this bundle concept, right, to develop the SkyNet model itself. Okay, and so here I quickly mentioned it. We had the auto DNN engine. Okay, so then here we use the bundles, and then we actually evaluate the bundles. So we come up with different bundle structure, and then we insert a header and a tail, and then we use kind of some data to quickly train them and evaluate them. Okay, and so then the search space on the DNN side is really depending on how many bundles you can search. I remember we searched maybe close to 100 bundles, and then eventually peaked about 20. Okay, but of course, this really depends on the particular target as well. Okay, so in this paper, we use the object detection as the driving application. But let's say if you're doing something else, right? So then the bundle probably will be designed differently, and there maybe the design space can be larger, right? So this is mainly a design methodology, right? And then in the same time, we also want to make sure when the bundle is designed, we can run auto halo synthesis on top of it. So, so this provide the flexibility, and then we can evaluate its hardware performance as well, right? So, hope this answers your question.
Yeah. Yuan Yu, thank you. So maybe Yuan Yu, if you have further question, you can type. I'm gonna speak your question later. So now I'm gonna unmute some of you who already typed your question so that you can speak your question. Yonggang, could you speak your question? I think I already unmute you.
Yeah, sure. So thanks for Professor Chen for the wonderful talk. So my question is that at the beginning of this talk, you mentioned that there are different scenarios like cloud computing and IoT devices. So these are all the common scenarios that AI want to solve. But I think for most of your research, you will focus on FPGA. So but I think for IoT devices, maybe some edge GPU or GPU or CPUs may be the dominant devices. But you can correct me if I'm wrong here. And for the cloud computing, most of them are the GPU servers. So I just want to know that how can you extend your insight and experience of on FPGA to these different scenarios? So because if we I like this question because maybe in the future in my research I want to target different scenarios. I want to know what's the motivation for me to use the method on FPGAs. Yeah, I mean demo on FPGAs. Yeah.
Right. Yeah, that's a very good question. So the reason that we pick FPGA is because that it's a piece of hardware and you can do a lot of customization on top of it. And then you can quickly evaluate your design, right? So you map to the board, you can measure the actual energy, power, throughput, latency, right? It's a board level report, right? And also much faster than simulators, for example, right? And then, however, a lot of these methods can be extended to ASIC, okay? So I'm glad that you mentioned this. Actually, Professor Lin and I collaborated on one work. It's called Auto DNN chip, okay? So it has also has an estimator, right? It's estimate the hardware performance and all that. And then it has an explorer, right, to explore the design space. And it can support different type of platforms, ASICs and FPGAs. And so the design methodology can be used for different platforms. So of course, for FPGA, we have to honor the FPGA resource and we have to honor its BRAM capacity and all that. For ASIC, maybe you have more flexibility, okay? But then ASIC will probably have area constraints, power constraints as well, right? And the common thing is both of these designs will use IPs, right? So for ASIC SoC design, the IP reuse is very essential, right? So then you can see the IPs, if we are targeting deep neural network applications, those IPs are similar to the bundle, right? So this basically set up the foundation, and once you have the model for different target, right, for different hardware platform, and then you can define the design space accordingly, then you can definitely search that space and produce the hardware and algorithm simultaneously, for that particular platform.
Okay, thank you.
You're welcome.
So what's your time limit, Dr. Chen?
Typically, how long?
We are very flexible. I still see two more questions. So either we can stay on schedule in case you have upcoming meetings, or we can just.
Okay, let's finish the questions. Yeah. So
okay.
actually, I think this is a very interesting. Yes. Mm-hmm.
Thank you. Luke, would you like to speak your question?
I have a very similar question as so first thank you Dr. Chen for this talk. It's very good, and I have a similar question as you guys. It's about the role of the FPGA plays in the actual applications. Mm-hmm. So more specifically, what do you think is a more important hardware efficiency metric, like for FPGA, in terms of do you think latency or the throughput? Because like as you mentioned in the previous slides in EDD, so we have two types of structures. One is pipeline, which is more throughput friendly, but another one is a recursive structure, which is more latency friendly. But I think FPGA would have more advantage when you do the pipeline architecture, because you can truly customize. You can just you can truly release the customizability of the FPGA to fit each layer. However, in a lot of edge application cases where latency is more important, so what do you think that's the more important metric for the FPGA in the actual application? Yeah. So it's like latency or throughput.
Right. Yeah. Good question. So for I think we have to strike a balance, right? So For edge devices, typically latency is very important. We have to make the decision very quickly. But in the same time, we will have some throughput. So let's see, you have a Tesla car, right? So the Tesla will have 7 cameras, okay? So all of them are taking images. Right? Of course, we have to analyze the images very quickly, but you have to coordinate them, and you do need to consider 7 simultaneously, so which does have a throughput requirement. Right? So in terms of FPGA per se, typically people use FPGA for latency sensitive applications because FPGA is not really designed for high throughput. Right? GPU is, right, very high memory bandwidth and thousands of little cores. That's just designed for throughput. Right? So there's a reason why people are using GPUs in cloud for training. But for FPGA, you basically play a lot of tricks and you design it in a smart way, right, honoring the resource constraint and customize the way, trying to minimize the latency. And then if you can replicate the pipeline, right, and then you can increase the throughput a little bit, but not too much. Okay, so actually we have kind of an incoming paper. So yeah, we had a DNN builder, right, that was published 2 years ago at ICCAD.
Yes.
Yeah, at this year's ICCAD, we have a DNN Explorer. Okay, so it's a follow-up work of the DNN builder, where we will combine both pipelining and the recursive design into the same chip. Okay, so it's actually quite interesting. It's trying to balance these two. Yeah, so you know, if you are attending ICCAD, maybe you can attend that talk. Yeah, thanks.
Yeah, that's
Right.
great. Thanks. Thank you.
Thank you. I'm gonna take the last question, the last chance. So
Right.
with your pioneering effort in this direction, co-design, and also your practice in Spirit IoT, could you share your vision where we should look for the next order of improvement in the hardware acceleration efficiency? Thank you.
Wow, this is a very challenging question. So next order, okay, so of course, people are exploring this from different angle, right? So one angle is 3D, right? So 3D architecture, right? 3D stacking, and you know, you probably heard about this CALFAL center proposal from Intel, right? So it's focusing on FPGA, and there it just you know, trying to ask for novel 3D architecture for FPGA, but of course 3D can be used for other microprocessor design as well, right? It's a general methodology. Okay, so that can, you know, have a very high potential, right? So one direction is the kind of monolithic 3D stacking, right? So at the DAC 2020 this year, Professor Philip Wang gave a keynote, and he mentioned the 3D monolithic stacking, even with nanotechnology, right? So that's definitely an interesting direction. And then others would include, you know, novel accelerator designs and novel algorithm designs and some fast algorithms, and people even talking about kind of using different algorithms, right? So let's not use deep neural network because deep neural network is too costly, right? Too computationally expensive. So what are the other algorithms that we can use to still achieve the same goal, but with much less computation, right? That's also interesting. And then towards AI particularly, actually, I touched on this at the end, right? So here we can have, you know, a distributed AI, right? So this, you know, quite interesting if we have multiple, many edge devices. How do we coordinate them and achieve the goal, right? And heterogeneous large-scale AI, right? So all these can be very interesting, but in the same time can be challenging as well, right? So we can definitely work on this, and we can also collaborate, right? And continue the successful collaboration and move.
Look forward to it.
Yeah.
Then I can see your insight, your methodology here still can extend to those, right?
Yes, that's right.
Yeah, yeah. Thank you very much. And to stay on schedule, maybe we should stop here. And thank you very much, Dr. Chen, for your time and also the very inspiring talk. Thank you all very much for attending the talk. Yeah.
Thank you. Yeah, thanks a lot for the invitation, and it's my great pleasure. Okay, thanks a lot. And
Thank you. Thank you.
right. Okay, bye.
Bye.